So, I will continue my discussion with the duality theory and the complementary slackness conditions. So, last time I had showed you that if at optimality, this is the optimal value of the primal objective function, this is equal to C B, B inverse B, right. And so, this is nothing but your, because at optimality the primal objective function value and the dual objective function value are the same. So, therefore, we can also look upon the dual variables. So, this will, when you do the take the partial derivative with respect to B I, the ith component, this will give you the ith component of this, which is your y I star. Okay. And so, the dual variables can also be looked upon as the rate of change of the objective function, primal objective function, with respect to the right hand side values given to you, right. And we will continue, as I said, you can, as you go along, you will keep coming across many different interpretations of the dual variables. Now, again I want to write down the complementary slackness conditions. So, the because one can go on and interpreting them in many different ways, complementary slackness conditions, and I am stating them for the canonical form, right, for the canonical form, for the canonical form of LPP, yes. And this is, we said that this is xj transpose aj transpose y. So, this is y bar minus cj is 0 for all j varying from 1 to n, and for the dual where this will be yi bar ai x bar minus bi is equal to 0 for all I varying from 1 to m. Okay. And we said that if a particular primal constraint, a dual constraint is satisfied as equality, then the corresponding primal variable can take any value. In fact, it can take a positive value, but the other way, if this has a positive value, then this must be satisfied as equality, and if this is satisfied as inequality, then the corresponding primal variable must take a positive value, then it must take a 0 value, because the product has to be 0, right. So, one can also interpret in terms of slack. Say for example, here if you look at the nutrition problem, the right hand side specified the amount of minimum amount of ith nutrition that the adequate diet must contain. So, which means that here if this is strict inequality, that means the diet that you have chosen has this particular nutrient more than the required minimum, right. So, this will be satisfied as strict inequality, and then for the yi bar will have to be 0. That means the associated dual the price that you attach to that nutrient would be 0, or if you want to look at it in terms of this, also you can interpret the value of yi bar. So, this slack, that means if there is a slack here, then the corresponding dual variable must be 0. If there is a slack here, then the corresponding primal value must be 0, and so you can go on interpreting this way. Now, another way to look at, see, once when we prove this complementary slackness condition theorem, I showed you that for x bar y bar to be optimal for the respective problems, the complementary slackness conditions must be satisfied, and if the complementary slackness conditions are satisfied, then the by feasible pair x bar y bar, then the two solutions must be optimal for the respective. So, it is if and only if condition, the theorem that we proved. So, that means in other words, if x bar and y bar satisfy the complementary slackness conditions, then this implies that C transpose x bar, I proved to you, while prove this is this, the two objective function values are the same. So, now the idea behind developing alternate algorithm, a variant of the simplex algorithm, is the dual simplex algorithm. So, we will develop dual simplex algorithm. Okay, the idea is, suppose for some reason it is possible for me to obtain a dual feasible solution very quickly, because remember, for obtaining a primal feasible solution, you may have to resort to phase 1, phase 2 algorithm to come up to, because you do not know beforehand or right away by looking at the problem whether the problem is feasible or it has a and to how to get that starting feasible solution. So, sometimes it may be possible to obtain y bar without much effort. In that case, the idea would be that, and so when you can obtain a basis, so in other words your y bar is obtainable as CBB inverse, right. And by the way, let me also point out here that suppose x bar corresponds to the basis B, that means x bar is the basic feasible solution corresponding to B, then we say that CB B inverse is the complementary, yeah, this is important terminology, complementary dual solution. Okay. So, given a basis for the primal problem, the CBB inverse will give me the complementary dual solution, and when you take y bar to be this, then you see the two objective function values will be satisfied, because for the basis B, the value of x bar is B inverse B, and so the corresponding coefficients, when you multiply with, you get the value C transpose x bar, and if you take your complementary dual solution as y bar equal to CB B inverse, then you see B transpose y bar will give you the dual. So, when you have complementary pair, there is another word one can use, when you have a complementary pair of primal and dual solutions, the objective function values are the same. Okay. So, we saw that if there is a basis which gives you a feasible solution such that that basis also gives you a feasible solution for the dual, then the solution is optimal, because dual constraints are nothing but optimality criteria. So, if your y bar equal to CBB inverse is dual feasible, then the current basis will give you a primal optimal solution, and therefore, it will also give you a dual optimal solution, right. So, this is the relationship between the two. So, then the idea here is that if I have a basis B which is dual feasible, that means the y bar satisfies the dual constraints, or in other words, I have a basis for the primal problem which satisfies the optimality conditions, but it is not feasible. That means this solution here, and what does it mean? So, suppose we have a basis B for the primal which is not feasible for P, but is feasible for D, for the dual problem, right. It satisfies the duality constraints. Then can we obtain a primal optimal solution? This is the question. So, starting with a y bar which is equal to CBB inverse, can I work for primal feasibility? So, this is the idea behind dual simplex algorithm. If you have a basis which is dual feasible, then we maintain dual feasibility and we work for primal feasibility. So, that means the moment I have obtained a primal feasible solution, I stop, because then, because of the complementary slackness conditions, I then have a dual feasible solution and I have primal solution such that the two objective function values are the same, and so they must be optimal by my complementary slackness condition, right. Let me repeat. So, what we are saying is that if I maintain, in other words, in the dual simplex algorithm, I will start with a basis which is dual feasible, and if it is dual feasible and then I work for primal feasibility, I all the time maintain this. I all the time maintain this, and therefore, at the end when I end up with a primal feasible solution, I have an optimal solution. So, this is the idea, right. So, let me explain to you with respect to a tableau, and then we can work out an example. Okay. So, if I remove this here, yeah. So, the idea here is, see, suppose you have your Cj minus Zj, which are all greater than or equal to 0. This is your right hand side, right, and then I have the column Yj. So, let us say you have Yrj, and essentially we will need the row here. Yeah. So, you look at this, and here we have Br bar, which is less than 0. So, that means for the given basis, for this basis B, you have a primal feasible solution, because this number is less than 0. If this was non-negative, I would have a feasible solution. So, once you have this, and Cj minus Zj's are all non-negative. So, for the basic variables there will be zeros, for the others there will be non-negative. So, optimality criteria is satisfied. How do I proceed? So, first of all, my idea would be to make this non-negative, and so therefore, I need my pivot element to be less than 0. Okay. So, I will divide by Yrj throughout, which will make this number Br bar, let me write it nicely, Br bar divided by Yrj. So, this becomes now positive. Br bar is, because if it was 0, I would not bother. So, only when it is less than 0, I bother about it. So, Br bar upon Yrj becomes positive. I divide throughout by this. Then, so that means I decide the exiting variable first. The exiting variable will correspond to a negative value of Br bar, fine, and then among the corresponding row, I choose the pivot element will have to be a negative element in this row. So, now I decide about the incoming variable, or the column which will enter the basis. So, since we want to maintain dual feasibility, what is the idea? See, how will this change? Because if I make this a pivot element, then I have to make a 0 here, which means that this whole row gets divided by Yrj, and then you multiply it by Cj minus Zj and subtract. So, a typical this thing, how will it look like? This will be Ck minus Zk, some other entry if you take Ck minus Zk, then the corresponding element here is Yrk, you have divided by Yrj, right, and then you multiply by Cj minus Zj. So, this will go to Ck minus Zk minus Cj minus Zj into Yrk upon Yrj, right, and we want this to be non-negative. Now, I know that Yrj is negative, so minus of that becomes positive. Cj minus Zj is non-negative. So, if Yrk is greater than or equal to 0, no problem, right, the sign will continue to be non-negative. So, I do not have to worry, it is only the negative Yrk, but if Yrk is less than or equal to 0, the sign can change here, right. If Yrk, then we require that Ck minus Zk minus Cj minus Zj into Yrk upon Yrj should be greater than or equal to 0, which implies that, see, if I will divide by Yrk, which is a negative number, then the inequality sign will change, which requires that Ck minus Zk upon Yrk should be less than or equal to Cj minus Zj upon Yrj. And therefore, when you choose the pivot element to be Yrj, this ratio must be the largest among all ratios for which the corresponding entry here in this rth row is negative, right. So, in other words, the way you choose your, therefore, the pivot element element corresponds to max Ck minus Zk upon Yrk less than 0. So, the maximum among all these, that means first I decide on the exiting variable which corresponds to a negative BR bar, and then in that row I look for all negative entries, take the corresponding ratios and choose that as the pivot element which corresponds to the maximum ratio, right. And so, this will give me this, and once I do this, then I make a 1 here and zeros elsewhere as we do, and we do this for the whole tableau. Then what you get here will be a new dual solution which gives you new top row, you can say the dual solution only corresponds here. So, the top row will satisfy the optimality criteria, and we will look at this right hand side vector again. If there is any negative entry, we will continue with the simplex algorithm, right. Now, another thing, now you can also see how this number will change. So, the current value, if suppose it is Z, the objective function value Z changes to so Z, and then what happens here, you have divided by Yrj and then multiplied it by Ck minus Zk to subtract. So, this becomes Z minus Cj minus Zj into Br bar upon Yrj, right. And here you see this is non-negative, this is negative, so this becomes positive, and this is negative. So, this is less than your Z. Yes. So, here what is possible is your Cj minus Zj may be 0, it is possible. So, we will say less than or equal to Z, right. So, the value definitely becomes lower, and why, and remember, okay, if you want me to write, maybe we will write minus Z, because that is what our convention is. The value here is always minus of the objective function value. So, anyway, this is becoming smaller than this, and when you take the minus of this whole thing, because that is the actual value, it is actually going up, right. When you multiply by minus sign, and this value will be bigger than Z, minus of this will be bigger than Z. So, why is that happening? Remember, because we are working with infeasible solutions for the primal. And now I want to, if some of you who have already become familiar with the simplex algorithm, you can see that we are actually solving the dual problem, but using the tableau for the primal problem, right, because primal feasibility implies dual, so primal optimality implies dual feasibility. So, I am maintaining dual feasibility, and the moment, and here primal infeasibility would imply that the dual solution is still not, the current solution is not optimal for the dual. So, when we work towards primal feasibility, trying to increase the primal, reduce the primal infeasibility, then the value of we are actually solving the dual problem, and that is why they see the pivoting, this becomes your pivoting column is actually a row which is the column for the dual problem, right, because the matrix for the dual problem is transpose of the matrix for the primal problem. So, these are the things which I am just pointing out, and you can sit down and look at them carefully. So, therefore, your dual problem is a maximization problem. So, since I am maintaining dual feasibility, the value of the objective function will increase. Okay. Now, quickly let us see. So, what can happen is, what are the outcomes, possible outcomes? Possible outcomes. What are the possible outcomes? One, we arrive at a primal feasible solution. Primal feasible solution. or if I arrive at a primal feasible solution, then I am done. I will say that I have an optimal solution for the primal as well as optimal solution for the dual, right. Second, and suppose we may face dual degeneracy, right. That is, your Ck minus Zk, your Cj minus Zj may be 0, but since you do not have primal feasibility, you will continue working for primal feasibility. So, the entry here may be 0 for the pivoting column, right. So, we may face dual degeneracy, and then possibility of cycling. Same thing. See, remember, you are working with basic feasible solutions. So, you go from one basis to another, but if you have degeneracy, it is possible that you may cycle. So, now here maybe right now I can yeah. So, you have to revise or modify. So, modify Bland's anti-cycling rules for the simplex algorithm. Which should not be difficult. Remember, all Bland says is that the first choice in each case has to be made. In other words, so I will not write it down, maybe you can, or okay, maybe we need to do it, fine. So, I will quickly write down. So, what will be the first, say for example, if you have this less than 0 and you have another entry less than 0 here, it is possible of infeasibility. When you have primal infeasibility, you may have more than one right hand side number less than 0. So, what will it be? So, what would be the first rule? So, Bland's rules for dual simplex algorithm. Okay. So, what would be the first? For the exiting variable, choose the row with the smallest index. Okay, it has to be unique. Remember, that is what Bland said essentially. So, a unique choice is that out of these I will choose this one, because this row has a smaller index. So, it should correspond to the same thing again. Maybe this is a little simplification, but what we understand by this is that the outgoing variable has to be the smallest index basic variable, right. Okay. This is this, and then second one for in case of max ratio tie, choose the smaller index column. Okay, so simple. Should not have been difficult for you to also sit down and modify it yourself. Okay. So, that means here again, if suppose I take a ratio here and I take a ratio here, both of them are equal and they are the max ratios. In that case, I will choose this one to pivot on. Okay. So, these are, so once I do this, so then we may face dual degeneracy, possibility of cycling, modify Bland's anti-cycling algorithm rules, and then for the simplex algorithm. So, then you will prevent cycling, and hence the algorithm, therefore, the algorithm will terminate in finite number of steps. And why finite number of steps? Because again I am working with the basis for the system Ax less than or equal to Bx greater than or equal to 0. So, the number of bases is finite, and since I am using Bland's anti-cycling rules, I will not use a basis more than once, and therefore, the algorithm will terminate. Okay. Now, what is the other possibility? What is the other possibility? Other possibility is that, since you see, remember, in order to create this, to remove this infeasibility, I needed a negative element in this row to pivot on, so that when I divide by this, the new variable that is coming in its place has a positive value. So, but then it is possible that I may not have any negative entry here. All entries may be positive or 0. Then I cannot proceed with my dual simplex algorithm. And what does that mean? That will mean that the dual problem is infeasible, is unbounded, and if the dual problem is unbounded, the primal is infeasible. We have already looked at it, right? So, I said that possible outcomes 1, 2, and then let me, so the third outcome will be all entries in the row corresponding to the exiting variable are greater than or equal to 0. Right. This would imply, as I told you, you cannot proceed with the dual simplex algorithm. This implies the dual is unbounded. Okay, which would imply the primal is infeasible. Is okay. I think that this takes care of almost all the aspects. If there is something left out, we will come back to it. But anyways, and now yes, this again I leave as a exercise. Find the direction along which the dual objective function value goes to plus infinity. Just like in the primal, I showed you how exactly you show that there is a direction. So, here also you should be able to show the direction along which the dual objective function value can be made as large as we wish, and the any point on the direction remains feasible for the dual. Okay. So, this is what you have. So, let us quickly take up an example. Yeah, suppose you have this problem. Minimize z equal to 3x1 plus 2x2 plus x3 plus 3x4 plus 4x5, okay, subject to 3x1 plus 5x2 minus 6x3 plus 2x4 plus 4x5. Now, the inequality is less kind. So, I will add a slack variable here, which will be x6. This is equal to 27. So, x6 is a slack variable, and therefore, it does not appear in the objective function because the coefficient is 0. Subject to this, then you have, see, the next inequality is greater kind. And remember, I am trying to find a basis. So, therefore, I will try to construct a unit matrix among the constraint set, right. So, I will multiply the constraint by, this is just to save time. Now, you can in fact rewrite minus 2x2 minus 3x3 plus 7x4 minus 6x5. So, once I have made it less with minus 2, right, then I will add a slack variable. I hope You understand what I am trying to say? Okay. Fine. The constraint was greater kind. I multiplied it by the minus sign. So, I made the constraint less kind, and then I add a slack variable, because I am looking for a basis, the starting basis, okay, which will be convenient. I can immediately compute my dual solution. Then the third constraint is also greater kind. So, I will multiply by minus sign, minus 9x1 plus 4x2 minus 2x3 minus 5x4 plus 2x5, and so I will add a slack variable, and this will be minus 16. Yes, and all xj positive. Now, for all xj greater than 0. Okay. Suppose you have this problem. So, you can see that here, because my starting feasible solution, the starting basis is I, my B is I, right. Therefore, your corresponding dual solution, complementary dual solution, CB B inverse. So, this is CB B inverse, this is of course all 0 0, because your CB is 0, right. But what about your Cj minus Zj? So, since CB B inverse is all 0 0, therefore, this is all 0. So, this is simply Cj for all j. This is right. Yes, I am hurrying up a bit, but does not matter. This is otherwise fine. So, because your B is I and your CB, your basis consists of slack variables whose coefficients, cost coefficients are zeros. So, all your CBs are zeros. Therefore, Y, your dual solution is zeros, and so Zj is all zeros. So, Cj minus Zj will be simply Cj's, and these are in this case non-negative. You see all of them. So, B is, this is the basis which is dual feasible, which satisfies the optimality conditions, but the corresponding primal basic solution is not feasible. Okay. So, this is a tailor-made situation where we can use the dual simplex algorithm to solve the problem, right. So, let us make the table and let us see how we proceed with the dual simplex. The steps are all clear, and we will use the, in case of ties, we will use Bland's rule. So, this would be, let us write down the table. This would be x1, x2, x3, x4, x5, x6, x7, x8. All right. So, this is 3, 2, 1, 3, 4, 0, 0, 0. This is your right hand side. The current value is 0, the objective function. Then you have 3, minus 1, minus 9, 5, minus 2, 4, minus 6, minus 3, minus 2, then 2, 7, and minus 5, finally 4, minus 6, and 2, 1, 0, 0, 0, 1, 0, 0, 0, 1, and your feasible solution is, the basic solution is 27 minus 2 minus 16. Okay. Now, by Bland's rule, as I said, this is the second basic variable, this is the third basic variable. So, we will choose the exiting variable to be the one which corresponds to the smallest index, right. Okay. And now, here you look at the negative entries and take the corresponding ratios. This gives you minus 3, minus 1, minus 1 by 3, and minus 2 by 3. So, this is the largest. For the negative numbers, the smallest one will correspond to the maximum ratio, right. So, here there is no tie, and therefore, this is your, so you decide on, you say that x3 will become basic and x7 will now become non-basic. Okay. So, let us quickly do the thing pivoting. So, this becomes right, minus 7 by 3 to minus 1 by 3, and you see this will become 2 by 3. Okay. Then you just simply subtract this from here. So, when you subtract this, what will happen here? This will be 2 by 3. So, 3 minus 1 by 3 would be 9, 8 by 3. Then 2 minus 2 by 3, 6 minus 2, 4 by 3. This becomes 0. The check is that now no entry here should become negative. If it does, that means you have made a mistake somewhere. Okay, you have not chosen the max ratio. Then this will be plus, so 9 plus 7, 16 by 3. Then this is 2, and this becomes 1 by 3, and this is minus 2 by 3. So, from 0 the value of the actual objective function has gone from 0 to 2 by 3. As I said, it should increase. Okay. Yeah. So, then yeah, we make zeros here, and that means you have to multiply this by 2, and so let us quickly just do this. Okay, I think what I will do is I will use the calculations done in my this thing, so that we save time. Yeah, so this becomes 5, 9, 0 as we have to do it, minus 12, 16, 1, then this is minus 2, and this entry becomes 31. Okay. Then here it will be minus 25 by 3, minus 25 by 3, 16 by 3, 0, minus 29 by 3, 6, 0, minus 2 by 3, 1, and this becomes minus 46 by 3. Okay. And so, here again now you have only one negative entry. So, this will be the exiting variable. Take the ratios, this is 8 by 25, 16 by 29, and this is minus half. Just check, this comes out to be the pivot element. So, I will continue with this. The numbers have become a little cumbersome, that is why I have not completed the tableau here, but in any case when you pivot on this, see what is happening is that I have shown the last row, the top row will remain non-negative, the numbers will become a little cumbersome, but here you see the right hand side is all greater than 0. And so, this will be the end of the dual simplex algorithm. Then this basic feasible solution will give me will be the optimal solution for the primal, and whatever dual solution I have here. Remember, this is your CBB inverse. I have shown to you last time that when you have a starting initial basis as I, then whatever you have here will give you the minus of the CBB inverse, because this is minus CBB inverse. So, minus of that will be your dual solution. So, what you read here would be your current dual solution, or among these columns what you have here would be your B inverse. You can compute the dual solution again, but in any case, because you started with the slack variables, this will be minus of this, the entries here would be your dual solution, this is your primal solution, and you have optimality because the two objective function values will be the same. Right. So, I will show you some more interesting situations here, and then later on also show you why dual simplex algorithm is really very useful, because when you do post optimality analysis and so on, we use the dual simplex algorithm comes very handy. You can use it. Let me now discuss the assignment sheet 3 with you, and the problems I have chosen such a way that they are little different from what we have discussed in the class, in the lectures. See, for example, question 1, it is an upper bounded variable problem, but we have lower bound constraints also. Okay. So, for example, you have x2, you have minus 1 less than or equal to x2 less than or equal to 3, right. Okay. So, in the class, in the lectures, I have not handled lower bound constraints, but it is not difficult, because since we have the algorithms built for non-negativity of the variables. So, here I can simply say that write x2 prime as x2 plus 1. So, that when you say that x2 prime has to be non-negative, this would imply that x2 has to be greater than or equal to minus 1. So, this lower bound constraint can be taken care of by making this transformation, and then insisting that x2 prime remains non-negative, which our algorithm manages without any problem. So, then this will happen. So, therefore, you will make the transformation x2 is equal to x2 prime minus 1 everywhere in your problem. You do this transformation, and that will make. So, what will be the new upper bound constraint on when you say that x2 has to be this is this, and this has to be less than or equal to 3. This will imply that x2 prime has to be less than 4. So, your new constraint, this one, gets transformed to 0 less than or equal to x2 prime less than or equal to 4. So, this is how you will take care of. So, you will convert the lower bound constraints to the upper bound constraints by the following transformation. Similarly, you will make a transformation for x3 greater than or equal to 1, right. So, similarly, if you look at problem 2 also has lower bound constraints, and I am asking you to draw the graph of the feasible region after transforming the problem. It is 2 variable problem. So, you can transform the problem and then draw the graph, and so your lower bounds will be 0. Now, you should be able to spot the redundant constraint here. Once you draw the graph, you will see that one constraint, if you remove it, does not change your feasible region. So, it becomes redundant, right. And then I want you to show 3 iterations of the bounded variable simplex algorithm using revised simplex. Okay. So, just try to see if you can sit down with the revised simplex algorithm, and for this bounded variable problem, try to just see how you will proceed. So, it will be interesting if you can, it will help you to understand. Okay. And so, this note that I have just explained tells you how to transform the problem from lower bounds to 0 as the lower bounds, right. Okay. Problem 3. Yeah, let us just read problem 3. So, I am asking you to give the dual of the following problem. Now, here I have x1 less than or equal to 0, and then x4 unrestricted. So, unrestricted you can take care of by writing x4 as x4 equal to x4 plus minus x4 minus. For x1 greater than or equal less than or equal to 0, you have to replace it by x1 prime, which is equal to minus x1. So, everywhere in the problem you will make the transformation, and then you have the in the regular form, and you can now write the dual of the corresponding problem, right. Then the following refer to a primal dual min max pair P and D. So, my primal is P, primal is minimization problem, the dual is maximization problem, and they are in canonical form, okay, which I have told you. So, provide a brief explanation with your answers. So, read the statements carefully. I will just go through 1 or 2 of them with you, and then you can. So, while solving P by the simplex algorithm, starting with a basic feasible solution, at termination either basis is dual feasible, or we conclude that the dual is infeasible, true or false. Okay. So, now I have changed the wording a little. Either you will termination either basis is dual feasible, which means that it is optimal. Dual feasibility means optimality of the primal, right, or that the dual is infeasible. What does infeasibility of the dual mean? Yes. So, figure it out. Okay, that is what I want you to. Then say, for example, look at look at problem 2 at the B part. For the linear program, minimize. So, I have given you the linear programming problem where the objective function is to minimize x1. You have certain constraints. X is the vector with the x1, x2 as the components. So, B is there now. Fine. Consider the basis feasible solution, basic feasible solution with a basis comprised of the columns of x1 and the slack variable in the second constraint. So, that means if you add the slack variables x3 for the first constraint, x4 will be for the second constraint. So, you have consider the basis consisting of the first column corresponding to the x1 and the fourth column corresponding to x4. Solve the problem graphically and the feasible region being unbounded. See, when you draw the graph, you will see that the feasible region is unbounded, but then it turns out that the objective function value is finite. So, I just thought I will give you, and you can yourself see that it is not necessary. I am asking you, give the associated complementary dual basic solution, right? You do all that. Then what can you say about this pair of primal dual basic solutions? Okay. So, what can you say about it, right? If P has alternative optimal solutions, is it necessary that the corresponding dual solution is degenerate? See, if P has more than one optimal solution, I am asking you, is it necessary that the corresponding dual solution is degenerate? So, try to answer it from the definition of the dual, or maybe construct an example where you can show either way. I mean, if you think it is true, then you should be able to construct an example, or if it is false, then also you should be able to construct an example. Okay. D part, Z star be the common optimal value of P and D. Okay, suppose we know it and it is finite. Suppose that x bar is a basic infeasible solution to P, whose complementary dual basic solution y bar is feasible, right. So, we know it is CBB inverse. If for x bar the basis is B, so it is infeasible, but the dual is feasible. Is it possible that C transpose x bar equal to B transpose y bar is Z star? Okay. So, you understand that I am asking you that the x bar, and by looking at the dual simplex algorithm, you have seen that you start with a basis which is primal infeasible and it is dual feasible, but it is not equal to the optimal value, the objective function, because you work for it. I had to do 2 iterations to arrive at the optimal solution for the corresponding problem, right. So, obviously, the answer to D is false, okay, that it will not be equal. Okay. Then the E part is, if P is unbounded, it is possible to replace the right hand side vector B by B bar and make it have a finite optimum. See, P is unbounded means that the dual is infeasible. If P is unbounded, the dual is infeasible. Now, what we are saying is that if you replace the vector B, right hand side vector, by the vector B bar, can you make the dual feasible? This is the question. And just think, does B have a role to play in the dual feasibility? If you can answer that, then you can answer this part. Okay. The final problem is exercise. Yeah, this is an exercise in writing the dual and then for verifying the complementary slackness conditions. So, here is a dual. Carefully, here is a linear programming problem. You have to write its dual very carefully, okay, because I have all kinds of constraints, equality, less, greater. So, you have to be careful in writing the dual, and once you do that, then I have given you prove that this is an optimum feasible solution by using the complementary slackness theorem, right. So, I have given you a primal feasible solution, and I am asking you whether you can, by using complementary slackness conditions, confirm or verify that it is also optimal. So, remember, when you have this primal solution, you will know which constraints are satisfied as equality. So, the ones which are not satisfied as equality, the corresponding dual variables will be zeros. So, you will have a smaller system. That means, you can now find a corresponding dual feasible solution. If you can find a dual feasible solution given this basis, then you can show that this is also optimal for the primal, and the dual solution that you find will be optimal for the dual problem. So, I have tried to make an assortment of problems so that you can, while you work them out, you will have a better understanding of the theory that we have discussed so far. So, this is up to complementary slackness conditions, and then we continue with the assignment 4 will be with respect to the dual simplex algorithm and other variants of the simplex algorithm. Okay.